This article is about the application of unmanned aerial vehicles (UAV) for autonomous exploration and surveillance. It was developed by our research group at Universidad de la República, Uruguay. UAVs are useful tools in many areas, including agriculture, rescue, logistics, surveillance, and others. Most of the existing applications of UAVs are based on remote control by a human operator. This means that UAVs are not able to perform an autonomous flight. In fact, one of the main limitations of UAVs is their flight autonomy. For low-cost UAVs, the flight autonomy is about 25 minutes, while battery charging is a slow process that demands about 1 hour. These problems can be mitigated using a fleet of multiple UAVs instead of a single one. A fleet allows cooperation among agents, for example, for covering the duties of any single UAV that must recharge its battery to maintain a constant presence in the air. In this line of work, this research proposed a cooperative intelligent approach for autonomous flight of low-cost UAV fleets. The distributed exploration and surveillance system has the following features. 1. UAVs must operate autonomously. 2. UAVs must be able to communicate with each other to exchange information. 3. The system must focus on maximizing the covered area. And 4. Certain points of interest must be monitored regularly. The proposed system is implemented over low-cost UAVs, Parrot Vivo 2, which is a specific contribution of our research because low-cost commercial UAVs are not conceived for complex systems, since they just offer a simple programming interface that only allows controlling the UAV by a human operator. A state machine is used for communications, location, and navigation, and a distributed greedy algorithm is proposed for flight planning. The autonomous exploration and surveillance problem includes several sub-problems. Exploration proposed to efficiently cover a known area, and it is a global path planning problem constrained by the priority of the point of interest to surveil and the flight autonomy of each UAV. In turn, cooperation between UAVs is needed without using a centralized infrastructure, such as a central server. Our proposal follows an agent-based approach where each UAV is able to cooperate with others in the fleet, and the communications are required for cooperation. Working with low-cost commercial UAVs pose additional challenges, but we aim at building a scalable and cost-efficient solution for practical surveillance of medium-sized areas such as educational, industrial, or commercial facilities. Regarding hardware, the used Parrot Vivo 2 UAVs have the Advanced Risk Machine version 7 architecture, and Vivo 2 use the VCBox Unix distribution, which has several limitations. It prevents users from executing certain tasks, for example, the network connection, or accessing the file system, or executing privileged operations. VCBox only grants access to a limited part of the memory and does not allow new programs to be installed and compiled directly from the UAV. So several alternatives were evaluated for program compilation. Among them, cross-compiling between x86 and ARM, which has specific drawbacks due to the limited capabilities of VCBox. We also explored using the QEMU emulator, which is difficult to install and configure in the UAVs. And finally, a third option was adopted. Programs were compiled in a general-purpose Raspberry Pi, which features the ARM architecture. In turn, when the Parrot SDK is not useful for developing, then the PyParrot library was used. But even in this case, PyParrot is not designed for handling a fleet of UAVs, so several modifications were required for using sensors and implementing the connection between the PyParrots and the UAVs. Regarding flight control and communications, the relative positioning method is applied for geolocalization. This method is based on the movements performed by the UAV. It is a simple method and does not require external sensors or devices, such as GPS or image processing. Two navigation modes were implemented. The first, navigation based on lateral movements, which is simple and accurate but limit the viewing area of the camera. And second is navigation based on rotation and forward translation, which allows the camera to be in a more natural position, 45 degrees, but it is a slower method because it involves an extra movement every time the UAV moves. Two communication methods were implemented too. Created an ad hoc master managed network, which required modifying the drivers of the network card in bebop2 to configure a leader UAV in master mode and the others in managed mode. And the other communication method used a Wi-Fi network covering the explored area, which also required modifying the default UAV interface of bebop2. This last mode can be used to take advantage of an existing network infrastructure and provides a robust communication method without a single point of failure. A specific information exchange protocol was developed for communication. The state machine that controls the UAV fleet has specific states for exploration, assigning point of interest for surveillance, coordination between UAVs, for example, to exchange partial information of the scenario to build a global map, low battery, and no connectivity states. The exploration algorithms are based on dividing the area to explore in square zones. The greedy strategy visits neighboring zones according to the time of the last visit. The region exploration strategy groups zones in 4 regions. The coverage of each region is evaluated, and the least visited zone in the least covered region is selected to be visited next. After performing a movement, the internal map of the UAV is updated to register the visited zone, and after that, the UAV established connection with other UAVs in the fleet for coordination and collaborative exploration. The experimental evaluation of the proposed approach considered a fleet of 3 UAVs and a flying height of 10 meters. The lateral displacement navigation mode was used, which provides a vision area of 10 by 18 meters, which is represented by a grid, and a mission time of 120 minutes is considered. The flying time of each UAV was set to 20 minutes, which is slightly lower than the flight autonomy of a bebop2. And both standard and critical alerts are considered to be generated by point of interest to be attended by the UAVs. The metrics evaluate the percentage of the map covered in the last 10 minutes, the percentage of the map covered by time, considering samples every 10 seconds, and the average, best, and worst response time to attend a standard and a critical alert from a point of interest. A random walk exploration strategy is used as a baseline method to compare the results of the proposed exploration strategies. All the reported results are average values computed over 50 executions of each exploration algorithm for each scenario. In this regard, several scenarios were considered, with different dimensions and position of obstacles. Scenario 1 is from a real facility from a company in Montevideo, studied with real UAVs. Scenarios 2 and 3 have larger dimensions and were studied by applying a distributed simulation approach using Sphinx, which is the official simulator by Parrot. A multiple instruction, multiple data parallel approach was applied, executed on a Xeon Gold with 128 GB of RAM from the high-performance computing infrastructure of our National Supercomputing Center in Uruguay. And the main results of the proposed exploration algorithm are reported and discussed next. Regarding coverage, all methods increased progressively the coverage of the studied areas until a certain limit. The greedy strategy obtained the best coverage results, which were larger than 90% for scenarios 1 and 2, and improved between 20% and 30% over the region strategies. The coverage value of the greedy strategies were highly robust, with a standard deviation smaller than 8% and a variation on the coverage in the 50 executions lower than 12%. Regarding surveillance, greedy also computed the best response time value for both standard and critical points of interest. In turn, the region strategy was slightly better than a random walk. Unlike for coverage, response time results are not as consistent between instances of the same scenario. The response time metric is significantly affected by the distribution of point of interest, and results show that no special distribution generated the best results. The improvement of greedy were up to 37.2% for standard point of interest and 51.8% for critical point of interest over random walk, and also up to 27.7% for standard point of interest and 43.8% for critical point of interest over the region strategy. These results imply that the time for effective surveillance reduced between 1/3 and 1/2 when using the greedy exploration strategy. Furthermore, the consistency of results and the difference in the response time metric between execution increased with the size of the map, suggesting that the greedy exploration strategy is more adaptable and scalable to face more complex situations. The numerics result for surveillance of point of interest are reported in the next slide. Summarizing, the main conclusions of the research included in the development of a distributed approach for autonomous exploration and surveillance using UAV, following an agent-oriented paradigm to provide an efficient cooperative solution to the problem. Coordination was achieved by a state machine for exploring and monitoring point of interest without needing a centralized infrastructure. The system was conceived to be used in low-cost commercial Parrot Bebop 2 UAVs, providing an affordable and cost-effective solution. 3 exploration algorithms were developed and compared: greedy, region-oriented, and random walk. The experimental evaluation was performed over real and synthetic scenarios. The greedy exploration algorithm achieved the best coverage and surveillance results, and the algorithm was robust and scalable to large scenarios. The main lines for future work are related to extend the experimental evaluation of the proposed approach, and also including intelligent navigation methods, for example, applying online image analysis and improved exploration, for example, learning to detect patterns from different scenarios. Thanks for your attention. I leave you with a short video by students Santiago Diaz and Bruno Garate.